Next, on Brownian motion, we're looking at reflection principle for Brownian motion. Reflection principle for Brownian motion as the fourth video on the Brownian motion videos. Okay, so first of all, we have a quick refresher of the idea of Brownian motion. So a standard Brownian motion, of course, like we've seen in the past three videos or so, is given as the collection of all BTs for t greater than or equal to 0, which satisfies the initial condition that B sub 0 is equal to 0. And then there are independent increments. And of course, BT minus BS is normally distributed with mean 0 and variance T minus S. And then it follows continuous paths. So the intuition of the reflection principle is as follows. If a Brownian path crosses a level A, we can reflect the path after the first heating time across the level. Okay? Then this creates a one-to-one correspondence between paths that exceed A, reflected paths that end above 2A minus X. Then this symmetry allows us to compute probabilities involving the maximum. All right. So that's the idea of the reflection principle for Brownian motion. And then we have in 5.3 the reflection principle, the formal statement for that. So let m sub t be maximum of maximum of value of bs for s ranging from 0 to t, and then for a greater than 0 and x less than or equal to a. So we then say the probability that m of t is greater than or equal to a, right, is and b sub t is less than or equal to x is equal to, so it's some kind of joint probability, and that probability is equal to is equal to the Brownian motion being greater than or equal to 2a minus x, 2a minus x. So probability that m of t is greater than or equal to a and b of t is less than or equal to x is equal to probability that b of t is less than or equal to 2a minus x. So the key corollary in this matter is this, that if you set x to be equal to a, if you set x to a, so it means you have 2a minus a, right? That'll be like a. So if you set 2 to be x to be a, it means that we have mt greater than or equal to a, and then bt less than or equal to a. So, and that means we just have probability mt greater than or equal to a is equal to 2. So we don't have 2p of bt greater than or equal to a, because this is 2a minus a, like that. So uh because mt is greater than or equal to a and bt is greater than or equal to a also, so we have 2 times probability that bt is greater than or equal to a. Since bt is normally distributed with mean 0 and time t, we can then say that the probability that mt is greater than or equal to a, probability that mt is greater than or equal to a is equal to 2 multiplied by 1 minus phi of 1, phi of a over square root of t, where phi dot is the cumulative distribution function. So this phi is the cumulative distribution function that you can get from the, yeah, if you have a kind of table, and if you're working online, you can also get it online. You can just Google and get the value like that. So as I'm going to show how you do that as we go on. So with that in place, then we can talk about distribution of the maximum. So probability that mt is less than or equal to a now is equal to 2 phi into a all over square root of t minus 1. So that's the distribution of the maximum. And the proof idea, just to give a hint of how to go about the proof, we first of all define the heating time tau sub a to be the infimum of s less than or equal to t, such that b sub s is equal to a. And then we define the reflected path bs tilde equals bs for s less than or equal to tau sub a, and 2a minus b sub s for s greater than tau sub a. Now this mapping is bijective and it preserves probability. So it maps paths with bt less than or equal to b sub t less than or equal to x to paths with b sub t greater than or equal to 2a minus x. So that's the idea if you want to prove all of that. So we can have example 1 now. So we want to compute probability that m1 is greater than or equal to 1. Probability that m1 is greater than or equal to 1. So using fact that probability of M1 greater than or equal to 1 is equal to probability that is equal to 2 times probability that B1 is greater than or equal to 1. So since B1 is normally distributed with mean 0 and variance 1, being because the t here is 1, right? So we can say that is 2 into 1 minus phi of 1. So that is 2 into 1 minus. Now for phi of 1, right, you can just go, uh, you can do CDF of 1. Let me see if that works. You can do CDF of 1. So for CDF of 1, right? Um, does it ever give it to us? So CDF, okay, let me just say CDF phi of 1. CDF phi of 1. Okay, let me go back. CDF phi of 1. CDF phi of 1. Okay, maybe I need to cumulative distribute cumulative cumulative distribution function distribution function phi of 1. Yes, so it's able to give it to us. So this is the whole story, and then phi of 1 is 0.8413. So if you check from the table, you get 0.8413. So I'll keep anytime I need any phi, I'll just come back and change the value and get the result like this. So it also gives the visual interpretation of that phi of 1. So you have 1 here and everything, it's cumulative. So everything that builds up to 1. So you have this whole region. That's why the probability is relatively high at 0.8413. That's 84%. So in that case, now we have 2 2 into 1 minus 0.8413. And if you subtract that, you have 2 into 0.1587. And that's approximately 0.3174. That's the probability that M1 is greater than or equal to 1. Now we have example 2 where we want to compute probability that M1 is greater than or equal to 1 and B1 is less than or equal to 0.5. So using reflection, then we can say that this is probability that B1 is greater than 2 minus 0.5, or better still, that's probability that B1 is greater than or equal to the sum of the two because they are facing uh yeah. So let me see the original thing. So greater than, less than, and everything becomes greater than as you have it here, 2a minus x, right? So in this case now, we then have 2a, 2 times 1 minus 0.5. So that is probability B1 is greater than or equal to 1.5. So now we need, so and for this one now, this is just going to be 1 minus phi of 1.5. Let me see, 2. Okay, if you have just M1 like this, it will just go like that. But if you don't have that, but if we have it in the original form, it's just probability 2a minus x. So but if x is equal to a, we just go straight. That is, if these two values are the same, so this is what we go for. But if they are different, we maintain the original thing. So here we just have because it has been reduced to only empty, because it has been, we only have that first one, M1 is greater than or equal to 1. So a and x are just 1. So that's why we have that double. So in this case now we have 1 minus phi of 1.5. So like I said, we can check that up. So phi of 1.5. So phi of 1.5 will be okay, this is okay, that's like 0.9332. 0.9332. And you have 1 minus 0.9332. That's of course what we have there. 1 minus 0.9332, like this. So that's 0.0668. So that's how we get this result. So the probability that this is going to happen is just 6%. That's 6.7% roughly. So in example 3 now, we have probability that M2 is less than or equal to 1. So in this case, that would just be 2 phi 1 over root 2 minus 1. And if you do all the evaluation, we get 2. Well, I mean, if you like, I can also do 1 over square root of 2, right? 1 over 1 divided by square roots of 2. So we take the phi of that, right? So yeah, that's 0.7602, 0.7602. So that's what you have here. So 2 times that minus 1 will give 0.5204. So, and then of course we can simulate all of that. So see what we got here was M1 greater. So when M1 is greater than or equal to 1, we can have this. But when M1 is less or than equal to 1, that's like 2 phi of uh you know phi of 1 over root 2, that's a over root t, right, is minus 1 like that. So and that's what we get. I think we have that expression. Yeah, this is it here. So distribution of the maximum. So this is where this comes in. 2 phi a root t minus 1. So in this case now, our the a is 1, the t is 2. So that's 2 phi a all over square root of t minus 1. And that's how we get that. So we can then, of course, simulate that. So we get left hand side and right hand side, because we're talking about reflection principle right here. But that's just ahead of what we are going to talk. So interpretation, and we verify numerically that probability that mt greater than or equal to a, mt greater than or equal to a is equal to 2 times probability that bt is greater than or equal to a. So the simulation should show both values are approximately equal. And just like what you see, this is like 0.3094 and this is 0.3168. They are pretty close. If you keep running, you keep getting, close values like that. Yeah, you can. I mean, the other time we got 3131, 3018, 3115, 3226. Then this 3057, 3122, 3101, 3188. Okay, so 3172, 3294. Okay, 3158, 30. Yeah, this is pretty close. 305 or 3062. So you can have something like that. And of course, so in this case, now this, since we're talking about reflection principle, you see the original motion is here now. So, and then it is reflected as shown in this orange graph up here. So that is exactly the idea of the reflection principle of Brownian motion. Okay, in summary, then we see that we see the key identity, that probability that mt is greater than or equal to a is equal to 2b, 2 times probability that bt is greater than or equal to a. So the reflection principle then converts path constraints into endpoint probabilities and relies on symmetry. Then it is fundamental in stochastic processes and finance. So we have problems that we can practice. So you can use any of the ones up there to deal with this. So you have, for the basic ones, you can just calculate probability that M1 is greater than or equal to 0.5. Let me see. Okay, I feel like taking one of each. So we want to compute probability M1 is greater than or equal to 0.5. Okay, probability M1 is greater than or equal to 0.5. Okay, so probability M1 is greater than or equal to 0.5. So here, um, for this kind of thing, right, we know this is greater than or equal to 0.5. So it is one-sided, I believe. That is going to be uh, is equal to 2 times probability that BT is greater than or equal to 0.5. Let me confirm that, because this is just one side now. We don't have both. So M1 greater than or equal to 0.5. That's this kind of case. That's 2 times probability that B1 is greater than or equal to 1. And that means that you are going to use this formula 2 into, yeah, we're going to use the formula that 2, we have 2 into 1 minus phi into A over root T, 2 into 1 minus phi into A over root T. That's the formula we're going to use in that case. So we know that m of t Probability that m of t is greater than or equal to a is equal to 2 into 1 minus phi a over root t, like this. Let me confirm for the last time. Yeah, that's when we have greater than 2 into 1 minus phi a over root t. So we need to identify all these components to get things in place. So in this case now, this is our a. So going by this now, okay, this will have to be B1, following M1. So so our A here is 0.5 as we have it here, and T is 1. So that means that probability M1 is greater than or equal to 0.5 will simply be 2 into 1 minus phi of A. A is 0.5 all over square root of 1, like that, because t is 1. So that means we have 2 into 1 minus phi 0.5 all over 1. Square root of 1 is 1. So that means we have 2 multiplied by 1 minus phi of 0.5. So that's the cumulative probability, right? So that's 2 into 1 minus. So we now need phi of 0.5. So I'll just go up there and switch. So this is now phi of 0.5, 0.5. So that just goes and we get that result. That's the value of phi 0.5 is approximately 0.6915. 0.6915. That's 0.6915. So that is 2 into 1 minus 0.6915 is the next thing. 1 minus 0.6915. 1 minus 0.6915. That is 0.3085. 0.3085. 0.3085. So now that is 80 plus 80, 160. That's 170. So that's 0.6170. So that is the probability is going to be 61.7%. So this, or 61.7%, that's the probability that will be um empty will be greater than or equal to 0.5. Okay, I guess I'll just stop with this example. So if you want to try the rest, just follow the formulas we have previously, depending on the kind of question. So you already have the different formulas. So we also took from the examples we took, or also we already took care of this. So for m1 less than or equal to 1 now, so you have to use this the last, I think that's the last formula, right? So for m1, for less than or equal to 1, you're going to use 2 phi a over root t minus 1. So that's what you're going to use for that. Okay. So try your hands on those problems and see how it all goes. So you have 1 to 5 for the basic problems. You have intermediate problems here, which will involve. So now that A and X are not the same, then you have to use the this other problem. This one now, I think that was the second one we did. Yeah, this one right here. So you need to use that. So that'll be 1 minus phi a over root t. So that's what happens here. 1 minus phi a over root t, and so on and so forth. So try. Just keep trying. Then for maximum distribution problems, that's also, we also did some, that was the last example I think we did right here. Yeah, I think, yeah. Okay, it's the same with this, I believe. So let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much. If you have not subscribed, why not go ahead and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you special privileges like getting to see some videos first, or being the first, or watching some videos exclusively as a member of the channel. You can also request for PDF copies of my notes. so that you can actually, work with them if you like. Then, of course, we can hang out together virtually or physically if you're in the same geographical location. We can meet physically to discuss whatever interests you on this channel, be it mathematics, data analysis, data science, machine learning, scholarships, anything at all. Don't forget to try your hands on the practice problems. All right. So you have 1 to 10 here, and then 11 to 20. Let me know how. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.